So once again, just want to say good evening to everybody. I'm Joe Dele Carpini, the Science and Operations Officer. Rodney Chai will not be with us tonight, but he did help put this presentation together, so I want to give Rodney a lot of credit. He's our main guy for getting our event reviews done, and he was a huge help in helping with tonight's presentation. So I will take you through it, but Rodney also gets credit for helping put the slides together for tonight's webinar. So let's start with the August 17 rainfall bust. If you remember this, this was kind of during the heart of the drought, and this was our first chance at really getting a widespread beneficial rainfall across the region. And on the right, you can see the image of kind of what fell. It wasn't very much. You can see kind of a little bit of a hole here in southern New England, amounts generally under a quarter or half an inch, and heaviest rains fell to our east across Maine, the Portland area, and to our west and parts of eastern New York, and especially parts of western New York. But up to a week in advance, the models were kind of flipping back and forth on whether or not we'd see a low tracking close enough to the coast to bring heavy rainfall, not unlike what we see in the winter with snowstorms. But once we got within about 24 hours of the event, all of the guidance really shifted closer to the coast, showed a potential really for 1 to 3 inches or more of rain across much of at least southeast New England. But the storm ended up being a miss, and heaviest rain fell up in northern New England, again, especially up toward Maine. So here's a radar loop. This was hour by hour throughout the day on August 17th. And you can see, notice how the showers are really kind of what we say fragmented and disorganized. Early on, you can see kind of the main shield of rain. It looks like it's over Cape Cod and the islands, but a lot of it stayed offshore and actually headed into Maine, you can see here. And as this was happening, it really was a clue to our forecasters that the guidance was really going to start backing off from what was earlier predicted. And we always tell the forecasters, when you see things like this happening in real time, we have a forecast of heavy rain and things aren't going according to plan, don't hesitate to make those changes right away. You're not going to lean on the models at that point. You're leaning more on things like radar data, satellite data, observations, to kind of adjust the forecast in the right direction. And, as a result, the forecast was trended drier, but it was kind of too little too late. So if this were a snowstorm, this would have been, a forecast of 3 to 6 inches or more of snow, and we would have gotten a dusting. So it would have been some disappointment there. So just going back, our forecasts are kind of collaborated with the Weather Prediction Center on a national scale. So they provide us kind of with a larger scale rainfall forecasts. We can go back and forth with them and, see where we need to make some adjustments. But for the most part, this is what you'll see here is the collaborated forecast between the Weather Prediction Center and our offices here in the Northeast. So this was the forecast 3 days ahead of time on Sunday. And you can see it was not too bad. The heaviest rain was south of New England and also, off the coast of Maine. A little bit of rainfall here, maybe upwards of about a half an inch. So that forecast was actually pretty good. And if we stuck with it, it would have verified nicely. As we got into day 2, notice still, not a bad forecast. The heaviest rain shifting up into Maine. Little, if any, rainfall in southern New England, probably a little bit too dry, but, had the right idea. The heaviest rains were going to stay east of the region. So again, this is Monday morning for essentially a Wednesday event. And then, kind of got a little bit strayed by the models here by day 1. Notice we've got the heavier rains a little bit closer to New England. Still not a horrible forecast. We had very little rainfall out in western New England, but definitely overdone on Cape Cod and the islands and the eastern Massachusetts coast. So we got swayed by the models, trending wetter at that point. So that's kind of the reason why the forecast artificially kind of increased here as we got closer to the event, which was actually the least accurate of the 3 days. So just to show you kind of what happened, might be a little hard to see, but this is looking at the HREF, the high-res ensemble forecast that we use, and it's usually very good inside of about 36 hours. Notice we've got a pretty, circular low-pressure system here off Cape Cod in the morning. But notice on the later run on the right, so this would be the evening run and then the daytime run, the low has shifted farther east. It's a little more baggy in appearance, which means you're going to have less lift across our region here in New England, and most of the lift will be centered farther to the north. So there was one clue right there, but unfortunately those daytime runs are coming in as the event is happening. So it's, again, kind of too little, too late. And if you see here on the rainfall, you can see that definitely is a clue here. Definitely a good blob of rainfall on the earlier run across the Cape Cod and the islands. Most of the rainfall is concentrated across Maine. And then on the daytime run, you can see a lot less rainfall here. Still a little bit too much on the Cape and Islands, but definitely the clue that the heavier rain was going to be up in Maine. You know, one thing we were looking at was, what is this here? Why is this such a blob? It's something called convective feedback. And on the higher resolution models, they operate at such a kind of a finer grid scale that a small error in, say, like a placement of a thunderstorm or two can really lead to larger errors than what we'd see off the kind of the global models. So think about what the HREF does, or the 3-kilometer NAM that we show, versus something like the GFS or the European model. These higher resolution models are often going to have these bullseyes that don't always come to fruition. So you can see a little bit, is kind of left over here on the daytime run because the HRF uses the previous run also. So we kind of think there was some convective feedback issue going on. It was developing thunderstorms offshore where in reality they really didn't happen. So it was showing quite a bit of rainfall over there. And then if we look at 850 millibars, or about 5,000 feet up, you can kind of see the same signal as we did at the surface. You've got a closed off low here on the evening run. A lot of moisture coming in down from Maine into eastern Massachusetts. But notice on the daytime run, it's a little more baggy in appearance, a little more open. There's less, moisture that's able to get in. So you still have a pretty good jet stream, low-level jet coming down. But this is more an indication you're going to have some dry air wrapping into the system. Whereas a closed system like this, it's going to have a better moisture feed around it. And just to show this, also showed on the global models, again, might be a little hard to make out the land here, but this is Massachusetts, Cape Cod, and the islands. You can see on the GFS, it's got a pretty pronounced closed low, as does the European, as does the NAM. But notice the lack of blue shading, which is the really deeper moisture across the area. On the GFS, it's located offshore. The European, it's well into the Gulf of Maine, and even the NAM, has a little bit on the Cape and Islands, but most of the deeper moisture is centered across Maine, well to our north and east. So also the lack of a strong temperature contrast this time of year. Remember, it's August. It really doesn't, it will not give us a lot of strong lift. So that was also a factor, really the lack of strong temperature contrast, which isn't unusual in the summertime, but just a lack of higher moisture over the region because the upper low was that much weaker. So looking at the analysis, you can see, in fact, this is what happened. We had a low was very far offshore, and the deeper moisture, as a result, was also located well to the east. More of a northerly flow, which was kind of bringing in some drier air well around the periphery of the system. So in summary on this event, the models often will struggle with precipitation on the northwest side of these low pressure systems during the summer especially. And as I mentioned, it's the result of a lack of a temperature contrast and some of the other convective processes that are more common this time of year. It's the model's almost trying to simulate a winter storm during the summer, and it doesn't always work out that way. But we thought really that the main culprit was a fair amount of the mid-level dry air. We didn't have the deep moisture in there. Also, some of the possible convective feedback issues, thunderstorms being developed in areas where they really didn't happen. And whenever you see these drastic shifts from run to run, it really should serve as a red flag. Our forecasters were kind of saying, why is it all of a sudden coming in so wet with, a little bit more of an open system? And it's kind of hard to figure out what's going on. But whenever we see these kind of drastic shifts, it doesn't lend a lot of confidence to the model solution. So in some cases, like happened here, you don't really know what's going to happen until the storm is showing up on the radar, which can be 6 to 12 hours ahead of time. So just remember that. This is especially true as we go into the wintertime if we start seeing these big shifts. All right, so moving on to the next one. This was a little more interesting. This was the August 23rd flash floods and also a possible tornado. We'll talk about that, two tornadoes. So here's our reflectivity loop going from about noon to 7:30 in the evening. We've got thunderstorms moving across southern New England. Did produce some flash flooding in greater Providence and also just over the border in southeast Massachusetts. And also we had a report of a possible tornado in Mansfield, Connecticut. So let's go and take a look at kind of what happened on both sides here. So here's a look at the radar estimated rainfall. This kind of shows a nice picture. You've got thunderstorms in essentially northern Connecticut, Rhode Island, and southeast Massachusetts, dumping some locally heavy amounts of rain, 2 to maybe 4 inches. But this is what really sticks out here. In just over the border from Rhode Island, you've got an area of greater than 5 inches. And we'll talk about that in a minute. But a lot of the rainfall stayed really to the south of the Mass Pike. Areas farther to the north got little, if anything, from this event. And 24-hour rainfall, we had a total of 7.44 inches in Rehoboth. These are looking at the Kokoraz rainfall observations. Note also 4.65 in East Providence, 4.64 in Pawtucket, and 3.5 in Central Falls. But interestingly enough, this report of 7.44 inches was from two of our employees who live in Rehoboth. One was Nicole, our senior service hydrologist, and he actually took the observation. And she actually made some nice documentation in her comments the next morning from her station in Rehoboth. She said, knowing this is a high number, sometimes these numbers stand out and people think they're erroneous, but no, it was right. A lot of people in town measured about 7 inches of rain from just buckets and things like that. But she reported a lot of basement flooding in town with some minor flooding even at her house. And the last time there was any flooding to this degree was in the floods of March 2010, so it's been a while. She tried to drive around town, but the flooding was fairly deep, and there was a good sheet flow, meaning the water was rapidly flowing across the streets. And driving her Prius, I guess, wasn't a great idea, so she decided not to do that. But fortunately, a lot of the streams and rivers had been extremely low to the drought, but they came up right to pretty much to bankful, but not end up flooding over the roads. So interesting that this all fell within about, I think, a 3-hour period. So really, really extreme rainfall rates over Rehoboth from this event. So I'm just showing some of the other flood pictures we got from some of the media and some folks in the area. Gano Street in Providence. Flooding on 195 West in Providence. You can see traffic was brought to a halt. The water was too deep to go through in that area. East Providence, it's maybe a little blurry, but you can make out it's up to the depth of the car doors here on the left. And also in East Providence, typical underpass type flooding there on the right. This guy, I guess, did make it through. Not a great idea. The water was over his hood in the video, but did make it through. All right, so one of the things that we look at when we talk about flooding, we use this MRMS. It's called multi-radar, multi-sensor. You can Google this and find it online yourself. But one of the things we look at for urban areas is what's called hydrophobic unit stream flow. What does that mean? Hydrophobic means areas that kind of resist water. So think about concrete, the urban areas, pavement, things like that, that will not absorb the water. So this gives us a really good idea of the potential for flooding in urban areas. And you can see over Providence, it did a pretty good job. So usually we start to become concerned when these values get into the orange, about the 300 to 400 value is what that is. And you can see in this case, we're well over that. The purples are 600 to 1,000, and the white is even above that. So there's the link there on the right, mrms.nssl.noaa.gov. And you can go right to the product viewer from there. So this really works well, again, for the urban areas and shows pretty nicely that corridor of heaviest rains through Providence and over into the Rehoboth area. We can also use various stream flow ones to actually look at the flow on the streams. But in this case, when we're looking at a high urban area, Providence, Hartford, Boston, Worcester, New Bedford, we kind of look at this hydrophobic unit stream flow. It's a much better indicator of the flash flood potential there. And you can see here, Andrew Lecanto from our office tweeted this out, showing between 3 and 4.5 inches of rain fallen, in that area. So the storms were yielding kind of instantaneous rates of up to 4.5 inches per hour over the same area, which was leading to a lot of flooding. And we're able to issue a flash flood warning for that area for this event. So remember that also the flash flood environments are also tornado environments if you've been with us for our severe weather or our tornado webinars. So we did have a couple of images here. Josh Singranelli actually chatted us up and showed this, what looked like a tornado out in Mansfield, Connecticut around 12:45. And on the right, Ryan Hanrahan had video sent to him of a water spout. This was on Long Island Sound between Orient Point and New London, which was shot by someone on the Cross Sound Ferry. And you can see it's actually making contact with the water. So this is a water spout. On the left, it's a little more difficult to see. Of course, we've got our trees in the area. We did look at this video very closely. We didn't see any connection to the ground. We didn't see any indication of debris being lofted, but it definitely was a funnel cloud. So let's take a look at that and kind of see some of the clues that we had on the radar in the environment. So this was about the time of the Mansfield funnel cloud at about 12:34, a little bit before. So on the left, we're looking at our reflectivity. On the right, we're looking at our storm relative velocity. So we're looking at the velocity, but subtracting out the storm motion, which is going to show us our kind of the rotation within a storm. And you can see we've got a nice little bit of what I would call an appendage. And, being this far from the Taunton radar, we're up about 6,000 feet. We're not going to really see a classic hook in most cases. We often just see something like this. You can kind of make out it's trying to form a hook. But in the velocity data, there's really nothing going on. Very weak velocities, if 10 knots inbound, outbound, if that. So not a lot of strong rotation at the lowest levels, and there really wasn't much above that either. Something that we look at on the bottom left is our ZDR, our differential reflectivity, and this can point to us where we have updrafts in the storm. So when you see these yellows and reds, these are updrafts, but notice they're very, very narrow. They're not very strong, wide updrafts. So we don't have a lot of upward motion in the storm. And looking on the bottom right, this is our correlation coefficient. Remember, we look for lowering kind of in the blues for an indication of something touching the ground, and there's really nothing there either. You've got some false returns. This is just an echo-free area that you're seeing it there, and that's nothing lowering going on. So in this case, about 10 minutes before that picture was taken, it's looking a little, I would call a little funky, as we like to say, but nothing that really stands out that say that anything tornadic is going on. And at 1240, it looks a little bit more interesting. Now you're seeing what looks like a hook trying to form, definitely. Again, we're looking up about 6,000 feet over Connecticut. And now you're starting to see a little bit of weak rotation. You've got a very pale green against some lighter reds. We've got about maybe 15 knots, which isn't going to really cut it, but there's definitely something going on. But notice the updrafts here have definitely become more fragmented. We're not seeing the reds anymore. We're seeing the yellows. So it looks like the inflow is probably getting cut off into the storm, which means it's not probably going to be able to develop a tornado. But, in here in New England, I've seen certainly better cases. We've had tornadoes in cases like this for sure. But in this case, it just doesn't look like everything's going to come together. But definitely this is an indication that there could be a funnel cloud at this point. Just probably not enough going on for it to touch down. And then at 12:45, this is about the time the picture was taken. Note we've got, again, a little bit of a hook. This is probably a mini, what we call a supercell. You've got a little bit of a hook forming there. Again, we're looking up aloft, not at the lowest levels. Still a little bit of weak rotation, but, at this point, it's almost becoming more convergent more than anything else. And, definitely seeing a little bit more of what we call a ZDR column, or, that updraft. It's shifted to the inflow part of the storm now. It's kind of located here, which means there could be a little bit of further strengthening. So this is something, you're going to start to watch and say, okay, possibly could start to strengthen and become severe, but nothing in the CC showing a lowering at this point. And then at 12:52, still has a bit of an appendage, but it looks like it's kind of losing, what rotation it has. Maybe a little bit of weak rotation here. Still seeing, some ZDR columns, narrow, but nothing really to say it's going to form a tornado anytime soon. So looks like it tried to do something as I put it kind of into a loop. Best, image was right here at 12:45, and then it kind of starts to fall apart a little bit at 12:52. So kind of close, but no cigar. All right, so our next one this was actually, we didn't have any pictures taken of it in northern Rhode Island, but it certainly caught our eye on the radar. So knowing it went through a kind of a populated area, I'm guessing there might have been a funnel cloud, but really no one, unfortunately, got any evidence of it. So again, we're looking at the same, 4 panels here. You've got what clearly looks like a hook here. There's almost a little bit of a boundary. This is either outflow or maybe even the sea breeze through West Warwick and up into Cranston. So something's definitely going on here. You can see there is some very weak rotation where that hook is. Again, it's less than 15 knots, so nothing that's strong enough, or not a tight circulation, but is there. And in the ZDR, you've got a little bit of a red dot right there. That's showing me a very small, ZDR column, indicative of kind of a weak and localized updraft, but it's there, and nothing, in the CC that's saying we have anything on the ground, but certainly something that's going to get your attention, and it definitely got our attention at the office. But as we look up, now I'm going to change the top panel here on the right. This is looking up at 3.2 degrees. We're up at about 8,000 feet. Notice that's where the rotation is. So it's way, way up. But it's kind of broad. Nothing, you've got some inbounds here, definitely bright, some outbounds there. The rotation's probably on the order of about, 25 to 30 knots, so that's good. It's just not together. We'd want to see this a lot tighter, but you definitely have what we would call a mesocyclone up in the mid-levels of the storm, but just not getting down. If I go back here, you can see there's just not anything happening in the lower level there with the rotation. It's all aloft, and we see that quite a few times here with these types of storms. You'll get the rotation spinning like a top up at 8,000 to 10,000 feet, but just never really makes it down to the ground. But in this case, to see the hook at low levels tell me, yeah, there was something trying to go. It just never really came together. So unfortunately, no one really got any pictures either, but my guess is we had a funnel cloud out of this as well. All right, so let's take a look at the setup, both for the flash floods and for the tornado environments, because again, they are very similar. This was the weather map at 2 p.m., and this is right out of the textbook for flash flooding, having a stationary boundary draped across the region, a warm, moist air to the south. We had temperatures in the 70s, dew points in the 70s. To the north, it's a little bit cooler. Temperatures are in the upper 60s, around 70 degrees, but all this warm, moist air is being kind of lofted over this stationary frontal boundary, which isn't moving. So this is our focus for showers and thunderstorms. And as you remember from the radar loop, they were tracking from west to east pretty much across this area here. And I can remember back from our meteorology school days, this was one of the classic setups, the stationary front flash flood setup, which happens a lot in the Midwest, but also can be favorable for severe weather or the isolated tornado. Again, remember, these storms are right along this boundary, and these warm frontal boundaries can give us our low-level spin, so help spin up these tornadoes along the front. So we'll take a look a little bit more at both of the environments. So if we look at the station plot, just to give a little bit more detail here, notice we've got south of the warm front, temperatures in the low to mid 70s. We've got dew points well into the 70s, 71, 73 on the islands. To the north, kind of a light north or northeast or even easterly flow, temperatures in the 60s to near 70. So this was providing us our lift just to the north of the warm front. So remember, our showers and storms were focused just to the north of the boundary, which is actually a common occurrence. Now, if we look at the mesoanalysis, a few things here. This is at 1 p.m. This is looking at our values of CAPE, or instability from the surface. So notice most of our instability is offshore, south of, say, Long Island, where it's about 1,000. Our values are higher down here. But notice the gradient of CAPE here. You've got a pretty big gradient across Connecticut, Rhode Island, southeast Massachusetts. And this is often just as important as the areas of higher instability. So think about it this way. We've got this unstable air south of the warm front. It's being lofted along that boundary. And where we've got this gradient is kind of where we're getting that maximum lift. So think about, we've talked about in winter storms, we've got a temperature gradient. That implies lift. The CAPE gradient can also imply lift across these areas as well. So this is our focus area where I've got outlined in black: Connecticut, Rhode Island, southeast Mass, maybe even up to the Mass Pike. So these are areas where storm development is actually pretty favorable. If we look in the lowest part of the atmosphere, this is in like the lowest about 5,000 feet. We look for CAPE in these areas as well, especially when we talk about tornado formation. You have to have that low-level instability to have these tornadoes spin up. And you can see, again, the maximum is out of the water, but we've got this really tight gradient over the same area, so that can be favorable as well. The one thing lacking, though, is the blue contours, which are surface vorticity or surface spin. We have to have some sort of surface spin up along that boundary to get a tornado to form. And look, it's not there. It's to the east, it's to the south, it's to the west. So that, to me, was a big red flag to say why we wouldn't get a tornado. Now, keep in mind, these values are over kind of a large area. You can always get local enhancements, especially due to terrain, especially in northern Connecticut, northwest Rhode Island, where you do have those hills. So it's, not to say you can't have it, but overall the environment was not favorable for tornadoes in this situation. And then if we looked at, what's called the effective shear, so this is our change of wind direction with height. And this is at the effective shear is kind of what the storm would feed in. It takes into account how tall the storm is. So it's showing, 30 to 35 knots, which is actually pretty good. I would say, this would be pretty favorable along with that CAPE gradient. But knowing we didn't have anything at the surface was kind of a negative factor in this case. But overall, a good environment for strong or maybe even severe thunderstorms. But then again, we go to the lowest levels, and that's really important for tornado formation. So I look at the 0 to 1 kilometer, what's called helicity or spin, and we're looking at values of maybe 50 at most, and that's just not favorable on the larger scale. Really need to see values of 100 or greater. But as I mentioned before, you can get away with seeing this on this map because you might have some really storm scale, really localized interactions on the order of maybe a mile or a half mile. So think about hills or valleys again. Those really aren't represented on these maps because they're more of a larger scale. then down to that really kind of neighborhood scale that I talked about. Now, our precipitable water, this goes both into the flash floods and the tornadoes. So we had plenty of available moisture. So think about if you've got a value of 1.7 right over Rehoboth. Essentially, if you were to wring out all the moisture in the atmosphere, you'd have at least 1.7 inches of rain. Now, we know we got more because there were training storms. But whenever you see values of 1.5 inches or greater, especially 2 inches or greater, that's favorable both for heavy rainfall or flash flooding and tornadoes in our area. So you can see the axis was going right through that same area where we had the warm front, where we had the lift, and we had the instability gradient. So things really lined up right across that area. And of course, the one thing we want to do is get those clouds to the ground. So we looked at what's called the lifting condensation level. And just think about it as that's the area where the cloud base is going to form. So the lower the LCL, the easier it is for a tornado to touch the ground because the environment's moist and the cloud base is lower. So typically we look for heights of below 1,000 meters and really especially below about 750 meters. And we certainly meet that criteria here. The 750 contour is through western Connecticut. So these are all values lower, almost down to about 500 meters here on Cape Cod. So we definitely had the low level moisture, the favorable cloud bases. Just I think we were lacking that low level spin to get that circulation down to the ground, which ended up, it's a good thing, no damage. So in summary, for our tornado checklist, as I mentioned here, favorable, we had a lot of favorable factors. Instability was there, including 0 to 3 kilometer, which is what we want to see. We had favorable effective shear, the spin in the atmosphere, a lot of moisture, favorable precipitable water, the LCL height to get those cloud bases down. And we had the warm front nearby to help with, low level spin up. So things were trying to go, and they almost did. But as I mentioned, I think the two unfavorable factors there on the right, the 0 to 1 kilometer helicity on a larger scale and the surface vorticity or spin were lacking. So I think those are really the reasons why we just didn't get things to come together. So you really need almost everything to come together just right to get these tornadoes to form. And again, they can happen on a smaller scale than what you see on those SPC maps, but it was close, but kind of just didn't happen this time. So again, kind of grateful that there wasn't any damage. Those could certainly have produced some wind damage across both Connecticut and Rhode Island. All right, so with that, that's a look at both of our events. If you have any questions, I'll pause here. We can throw them into the chat, but kind of wanted to show you two quick events. One that didn't produce, heavy rain when we thought it kind of would, which was during the drought. And, we have a famous saying in the office, when in doubt, leave it out during the drought. But, we did think we were going to see some beneficial rains. But right after that event, we did turn the corner. And the second event there with the flash floods was kind of the first round of getting some beneficial rainfall as we got into the later portion of August and certainly into September. This month has certainly been wetter than normal, and we're recovering nicely from our drought conditions over the summer. So I will see if we have any questions. Let's see. We do have two. Let's see. Long question. That's okay. So let's see. First, for the August 17th bust, do you think the possible convective feedback in some of the models is also what contributed to the farther westward track of the low? Yeah, that's a great point. So like a positive feedback loop that contributed to the model forecast. That's a great point. I think it did, definitely. We see that a lot in the wintertime. For those of you who like to follow the winter storms, you'll always notice the higher resolution models, think about the NAM in particular, will always show the low surface low tracking to the west compared to maybe the global models, the European and the GFS, for example. And that's typically due to the convective parameters that are in the model. It's able to generate the convection on more of a local scale, which in turn creates a stronger surface low, which in track will help it tuck to the west a little bit more. So that's a great point. Something I didn't even think about until you brought that up. But yeah, it absolutely did. So once we lost that convective feedback error, notice the low track farther to the east along in line with the global model. So hey, great catch on that. Absolutely. And then for question 2, for the second event, do you think the stationary boundary is partially the reason why the velocity was so unimpressive on the radar, despite the funnel cloud being reported? And this is from our friend Sebastian. I say this because along the boundary, the soundings showed easterly surface winds with mainly, unidirectional or same flow above, meaning most of the spin is concentrated in the lower portions of the atmosphere where the radar might overshoot this. Yeah, that's a good point too, Sebastian. Remember, the gradient winds were fairly weak. I didn't show a lot of that. but we did have some shear, but down in the lower levels they were fairly weak. So you're right, the actual better rotation and better winds were aloft, which is what we saw in the northern Rhode Island storm up at 8,000 feet. Rotation was great there, but wasn't great down at the lower levels, and that you could see in the velocity data. Just wasn't showing up. So Sebastian, 2 great points, A+ for you today. You seem to really be catching on from our event reviews and everything with meteorology. So great catches. All right. And from Bert, a comment, South Sandwich got a 1/4 inch. 4 miles north of Sandwich got over 5 inches. And yeah, that's what happens when we have these, what we call convective episodes, very localized. Even that Rehoboth amount, 7.44, just a few, 10 miles away, there was less than 2 inches. So you got to be kind of in the right place at the right time to get into these. So, all right, let's see. I'll pause here just for a couple more minutes if you have any questions. These were pretty much, kind of straightforward event reviews. No real, the first one kind of was the interesting one because we don't often see a model bust like this in the summer, but they do happen. I think we see a lot more of these in the wintertime. We get frustrated because we don't get the snow that we always want to see. But yeah, I think the convective feedback in that first event was the main reason. Kind of led to just a series of errors in the models and brought things a little bit too close to us. And then, for the second one, the wind fields were just a little bit too weak that day. We didn't have the low-level spin in place, which really is what we need to kind of spin up these tornadoes. Remember, our tornadoes here most commonly spin up from the ground, believe it or not. There's rotation aloft, and it kind of links up with rotation from the lower levels. Where in the Midwest, when we get like our June 1st, 2011 tornado, it's all from the top down, comes down from the mesocyclone. So hope you guys enjoyed that. Okay, at this point, let's see. Okay, Sebastian's got another comment here. In some of the forecast discussions, the models also could have a tough time resolving the bust event because it was an anomalous and strange event. Yeah, that could contribute as well. When you get an event that's kind of out of the ordinary, the models have a tough time handling that. We know with an anomalous event, say, a high-end blizzard, we know, the models are going to have a tough time with things like the snowfall placement, things like that. So, yeah, this was an unusual event. We see them sometimes in August where you get a coastal storm, but yeah, it's out of kind of the normal or the climatology of the models. So the models can struggle with that in this situation. So yeah, another good point, Sebastian, definitely. All right, so I think at that point we are about good with this, and thank you for your questions, and hope you enjoyed our quick review of these presentations.